for example, we could say, even though the velocity does not stay constant at 7, the velocity is going up. If we were to think of the velocity as being constant for a couple of minutes, please.
What is the name of this unit?
So this entire unit I have titled Integration Using a Calculator. That implies that there will be another unit, Integration Without a Calculator, though it's not really a full unit, it's more like a kind of a mini unit as we merge into practicing the DAV test. So did we talk about this idea that if we assume the velocity stays constant for 2 minutes at 7 miles per minute, we could calculate that during that 2-minute period, the position of the plane would change by 14 miles. Did we discuss this last time? Yeah. Getting some nods, that's good. We continue that process over 5 minutes, a 5-minute time period. We learn that an approximation for how far the plane, like the change in position of the plane, would be 39 miles for the entire 5 minutes. Okay. Did we talk about that this process is known as integration? Yes? And integration is not really anything very new. It's just doing something you already know, kind of combined. So multiplying and then adding up the results of that multiplication, that's what integration is. Did I show you the symbol for integration? You got some doing this and some doing this. So there we go, the big S. We're taking velocity and multiplying by a change in time. So that symbol looks like this. Velocity multiplied by dt. It's a velocity value multiplied by some amount of time. That's what we're doing here. After we do the multiplication, we use the big S to indicate that we are adding them up. So we're starting at time equals 0 in this example, going to time equal 5. And what we're computing is the change in the position of the object during that time period. So it's a little bit different, but we're computing this difference. Questions? Awesome. Okay, one thing to make sure you make sense of, and please talk as much as you'd like. This integral does not become this. So don't think of equal as like, hey, here, this is becoming this. These two things are simply the same. So one way of computing, like think of it like, here's the object at time 0, wherever that is. Here's the object at time 5. And the distance between my hands is 39 miles, because that's how much the object's position changed during the 5-minute period.
So when you see a problem like the left side of that, and you automatically think, okay, I used the right, like that part to solve the equation? Is that right? Use the right side?
You're asking the right question. Let me say it back to you. So we're actually going to use integration for other things as well. So don't get kind of fixed on, we only use integration for this. This is one use. But commonly what's going to happen is the question might say, okay, during this 5-minute time period, what is the change in position of the particle? And if you have no information about the position, you're going to ignore this side of the equation completely. And you're going to say, I need to find the value of this integral. Once we discover that this integral's value is, say, 39 miles, we've answered the question without even looking at this at all. Because that's what the integral is computing, is that change in position. Did that answer your question? 2 points. Anyone else? Please, go ahead.
When you're writing it out like that, is it necessary to put the interval like you have t equals 0 and t equals 5? Will you write that out every time you write on an equation like this?
So whenever we're doing an integral, we must specify the span of the integral. So you don't have to write t equal. You can just say 0 to 5. Whatever is here, this dt, that indicates that this is a time value and this is also a time value. If this were dx, this would be x equals 0 to x equals 5. this were dy, it would be y equals 0 to y equals 5. So yeah, you do have to specify the interval. 2 points. But yeah. Okay, back to Porter's question. But it is crucial that you make sense of this idea as well. That another common thing to ask is to say, well, we'll just tell you in the problem that the position of the object at time 0 happens to be 10. So that information is simply given. They don't give a reason why they know that, they just give it to you. The position of the object at time 0 is 10. And you are expected to know how to use this equation. By the way, this equation has a name. It's known as the fundamental theorem of calculus. The name of the equation should, as Porter just said, lend some sort of importance to how much you will use this. Okay. I took an entire AP test is worth 108 points. I took the 108 points and I looked at every single problem and kind of counted up. I found that about 30 to 40 of the points available on the AP test use this theorem. So I reserve today to take whatever pace you need to be really comfortable with this theorem. So anything that comes to mind, just talk about it. Like, we can't spend too much time on this because it's literally a third of the test, this one formula, used in lots of different ways. So another way they use the formula is they'll say, hey, the position of the object at time 0 is 10, and they'll ask you to determine what is the position of the object at time 5. And what you'll do is you'll say, hey, I know this to be true, so all I need to do is a little bit of algebra, rearranging. I can add this symbol to that side and end up with a new equation that looks like this. And again, please don't just copy the equation. Get your brain to say, that makes sense. I understand what's happening. I'm not just copying. Please, Porter.
So how would you write it without any numbers? Would you just use x?
Sure. So you just say time equal A to time equal B. And then this would be time B minus time A. 2 points. You want to have a question how I got from the red to the purple? Please.
Well, I have a question how you said that those two aren't equal but they're the same. So then why are you able to add that away?
So one way of finding how much the position of an object changes is to simply know the two positions. For example, if I know S of 5, change color here. If I know S of 5 happens to be, that didn't work. Come on. So if I know S of 5 happens to be, in this case it would be 49. And I know the position at time 0 was 10, then I certainly can just subtract them and know how much the position is changing over that time period. But I don't have to know this at all. I can simply know how to do an integral, and by doing the integral, which is what I did up here, I compute the same thing, the 39. That's what I meant by saying they're the same. That doesn't mean I can't rearrange the equation to my advantage. See if this helps, Nikki. What this is telling you is, you tell me, where is the object located at time 0 according to what we've written on the board? 10. This integral is going to compute by what amount will my location change during the next 5 minutes? 39. So what's my new location? 48. That's all this is telling you. Did that make sense? 2 points. Anybody else? That's the key, what Nikki just did. Be able to read this and not just read an equation, but make sense of what the equation's saying. Hey, I'm located at location 10. The integral computes how much my position changes over the next 5 minutes. So now where am I? I'm at 49. Oh, awesome. they'll also ask, this is kind of back to Porter's question, how does this get used on the test? They'll also turn the question around and say, well, you don't know this anymore. Now what you know is the position of the object at time 5 happens to be 49. Create an equation that shows how to find the position at time 0. So what's that equation going to look like? Like, you're still just rearranging the fundamental theorem of calculus to come up with a new equation. So Porter's in. Who else can see it? Don't think too hard. It's not a hard question. Just like, what equation do I write that says, here's how I calculate the position at time 0? Anna's in, Ryan, Stephen, Josh, Adam, Josh again, Ethan, Mason. 2 points for everybody who's saying their name. Joe, Alexis, talk to me, Shirley.
So it would be negative S5 plus the big S equals S0.
Nicely done. And I'm going to reorder that just a little bit because it makes me talking about it a little bit easier. So this integral is going to compute the amount that the position, hold on, I messed up. 1 second. So first I'm going to say that at time 5, the position of the object is 49. And I just need to work backwards. So I want to take away from that how much the position changed. So I do the integral to find how much the position changes. That's the 39 value. And that's how I can figure out where was the particle at time 0. And it would have been at 10. Questions? Please.
Why wouldn't it be minus S5 and plus S? Just because we have to minus the S5 to get on the other side?
So we subtract this over, it's going to be negative S5 plus the integral equals negative S0. But we want it to be positive S0.
Oh.
So we multiply both sides by negative when it switches.
Okay.
Does the story make sense to you? The particle ends up being at location 49. We take away from that whatever the change in position was to get where we used to be. Okay. 2 points for sure. Anybody else? Awesome. Please. Right.
What's the V of t and d of t?
So V simply stands for the velocity of the particle, or the object, whatever. dt means change in time. And that's what we were doing up above, where we're saying if we know the velocity and we multiply by whatever amount of time that velocity persists, then we'll know that for that time period, this is the amount by which the object's position will change during that time period. Doing it repeatedly allows us to find how much the object's position changes over a longer period of time. 2 points. Anybody else? Solid. Okay, the fundamental theorem as I've written it here is applying to velocity. But the fundamental theorem applies to any rate of change. Velocity is the rate at which position is changing. If you say the velocity is 7 miles per minute, that means the position is changing 7 miles every minute. It's a rate, okay?
So then a position graph wouldn't be a rate.
Correct. So typically I will not integrate a position graph. There could be a reason why I need to, but for this class, not so much. Like I'm going to integrate a rate. For example, I could do this. 2 more for Porter. I could integrate from whatever time, 7 to 15. And I could integrate v prime. The symbol v prime represents the rate at which the velocity is changing. So according to the fundamental theorem of calculus, who knows what gets written here? So I'm trying to get you to connect what's really being said here with a new application. Here we're integrating the rate at which position changes, And the integral calculates the total amount of change in the position during that time period. So right here, if I integrate v prime, what gets written here? I'll pay everybody. Show me your hands. What gets written here applying the same thing, Landon?
Is it s prime of 5 minus s prime of 0?
True. We're going to write it as velocity, although what you said is not wrong. It's totally fine. So this would be v of 15 minus v of 7. And here's how I tell the story. I'm integrating the rate at which velocity is changing. Just read the name for me.
Thomas Ross.
Thank you. I'm integrating the rate at which velocity is changing. Therefore, the integral is going to compute the total amount of change in the velocity. Like if the velocity happened to be 100 meters per second at time 15, and the velocity was 75 meters per second at time 7, then I know that this integral's value is going to end up being 25 meters per second. That's another application of the fundamental theorem. How many knew I was going to write this before I wrote it? 2 points. Anyone want to talk about it? Please, Ruth.
So is the reason why you use v instead of like s prime is because velocity is the derivative of the position?
It's perfect. Yeah, writing s prime would be just as correct. But for telling the story, I kind of like writing v.
Okay.
But it's exactly the same thing. There's no difference. 2 points. Please, Grace.
I get why the s prime is the same as the v because it's like the derivative sort of, but then like in the original part, in the act like the integral, why did you do the v prime there when you did the v? Like I don't know what I'm
You're doing
saying,
just
but
fine. You're doing just fine. So on the previous page, what I had written was this. I'm changing around on purpose to make sure you can see the connections. So on the previous page, we wrote, if we integrate, I think we went 0 to 5, v of t, we're integrating the rate at which position is changing. That's what velocity is. So this is the same as doing this integral. Those two are identical, no difference. And when you integrate the rate at which position changes, you are calculating the total amount of change in the position. So I don't know if that answered your question, but those are the same thing. 2 points?
Will the AP test ever give a problem that includes like that's what it gives you as s prime?
Please, 2 points.
So with that top equation, can we put in a of t? Since
Genius.
that's the equivalent
That's what I was-
to v prime of t?
Genius. So this equation here is the same as this one. 7 to 15, integrating it, that's a terrible 15. 7 to 15, integrating acceleration. Acceleration is the rate at which the velocity is changing. Therefore, the integral finds how much in total will the velocity change during that time period. Perfect. Please.
This could be completely wrong because I don't know if I remember it correctly because it was last year. In physics, I remember my teacher saying, and this could be completely wrong, that like the derivative of acceleration is called jerk.
I've heard that as well.
Would we ever see J of t on a test?
No, they don't use that for AP calculus. But I have heard the same thing. So you're remembering it. Jonathan, I'm pretty sure you're remembering that. They just don't use that symbol for it. You may need to use a prime, but they won't use J.
Yeah, it's velocity, acceleration, jerk, something.
Yeah, it's some bizarre. I've heard that as well.
Yeah.
Anybody else? Okay. Next thing. Okay, Danica's chart helps sort this all out. Watch. You have position. Okay, make sense of this. Really, seriously, third of the test is this idea. You have position. If you take the derivative of position, you are creating a rate. Okay, you're creating a rate, S prime. And S prime is the same thing as velocity. Okay? If you go the other direction, you're using the fundamental theorem. Hence the name, fundamental theorem of calculus. But you don't really find the position. You find how much the position changes. So it's not like a pure opposite. Okay, you don't find the position, you find how much the position changes. That's really bad grammar, but how much changes, whatever. Order.
So for a fundamental theorem problem, there will always be a graph.
Good question. So I'm starting with the graph because I think it makes it easier for you to digest the meaning. But you'll see questions involving the fundamental theorem that only give you a table, only give you a graph, only give you a formula. Rarely will they give you two of the three. So, 2 points.
Why are we using S for position?
Just because they do. I don't really like the choice, but that's what they use. So just trying to get you used to it. 2 points. Anybody else? Solid. Here's another one you'll see often on the AP test. What goes here? Hands up, come on. According to the fundamental theorem, what goes here? This is just another application of the fundamental theorem. Austin? So some people ask me how many knew this? 2 points. I was asked quite a while ago that, once we find F prime, can you go backwards? You can go backwards. We'll learn eventually how to actually find an equation for F. Right now we're focusing on just finding this change in F, not F specifically. But there is a way to use the fundamental theorem to find F itself. So, questions? Awesome. Okay. Let me read this to you one more time. Okay. I want this to click again. 30 to 40 points on the test are this idea. When I integrate the rate at which F is changing, I compute a number, 217 or something. That number represents the total change in F over here, which means if I were looking at the graph, if this were true, and I were looking at the graph of F, I might see a graph where right here at x equals 6, the y value is, I don't know, 25. I got to do the arithmetic easier than that. Hold on. Like 20. And then over here at x equal 18, raise your hand if you know what this y coordinate has to be if this is all true. If we know this is true because this is the fundamental theorem, I'm telling you we do some problem in the future and this integral turns out to have a value of 217. Who can tell me what this y coordinate will have to be on the graph of F? I'm trying to make sure you can follow the story, not just copy what I do. So what's the y coordinate here? Maddie?
237.
How many knew that that would be 237? Show me. 2 points. Who wants to talk to me? Please.
Well, I don't know what to tell you.
That's good enough. 5 points for Shirley for raising her hand. Mark them down. The idea is that when we integrate the rate at which F changes, however we find that integral, the value of the integral, in this case I pretended it was 217, that's going to represent the total change in F between x equals 6 and x equal 18. So then I drew a graph of F and said, well, let's suppose that when x is equal to 6, the value of F is 20. So I just made an example where I figured out that F of 6 had to be 20.
Oh, and then you just...
You see it now?
Yeah.
Perfect. 2 points. I already gave you 5. That's 7. Good. Anybody else? The reason I paid Shirley so much is you just have to talk. Like if you talk about it, it'll make sense. And then you're all set for a third of the test. Like you really have the foundation you need. You need more, but that's the foundation. Other questions here? Okay, watch this. Please raise your hand if you can remember the other symbol that means the same thing as f prime of x. Just raise your hand. Who can remember another symbol that means the same thing as f prime of x? Show me your hand. What's another symbol, Grace, that means f prime of x?
dy over dx.
How many were thinking dy dx? Show me your hand. 2 points for that. Who think? Go ahead, Steve. What up?
My friend.
You can think of y prime. That's fair. 2 points for that. Perfect. df of x over dx. So I was thinking of those as well. But notice what happens. If I replace f prime with, watch me, d of f over dx, and we're multiplying it by dx. Nice! They don't cancel, they divide, right? They divide to make one, right? What are you left with? A big sum. Okay, what does d of f mean? Change in f. Means the infinitesimal. Look how cool this is. Okay? You have the infinitesimal. These divide out. Dude, you have the infinitesimal change in f. And you're adding it up over this time. You're saying, hey, how much does f change in this little time period? Plus, how much does f change in this next little time period? Plus, how much does f change in this next little time period? You add it all up, you get the total change in f. That's what integration does. What's that?
I said I just like to save on mine.
Oh, nice.
Writes down d f of x over
Yeah, no worries. Okay, so well, we're trying to get your brain to connect because it's the connections that lead to success on the test. Like knowing the connections makes them. It's the difference. Copying just doesn't help in this class. So what I said was we've been talking for quite a while now that the fundamental theorem tells me that if I integrate the rate at which f is changing, the result of that integral will be the amount, like the total change in f over some span. So this example said, hey, the integral was 217. F at time 6 was 20. So then f at spot 18 is 237, the total change in f. And then I showed you that mathematically that's exactly what we have. Because f prime means change in f divided by change in x. These divide out. All you're doing is adding up, the big S, little changes in f. Just like little by little. You're saying, hey, from here to here, f changes by 1. From here to here, f changes by 2. Add them all up, you get the total change in f. Perfect. 2 for Joe. Anybody else want to talk? Awesome. Okay, next thing. On your paper, on item 3, so page 3. Okay, I'll jump back and forth a little bit here. Page 3 summarizes what we just talked about. Okay, the fundamental theorem of calculus as it applies to velocity is right here. Here's the fundamental theorem rearranged, so you could solve for the position at time 40. We already talked about that. Any questions? Awesome. Go back to page 2 now. So page 2, item D. Okay, some new words here. It says, I don't honestly know the exact pronunciation. It says use the left Riemann Sum. I think it's Riemann, I don't know. Riemann. I believe it's German. Anyone speak German?
Ramen.
Do you know how they say it?
Ramen.
Probably like that. No, that's not right. I just don't have a good accent. Riemann's good enough for us English, American speakers, English speaking Americans. So, left Riemann Sum. Remember when we were doing this? I think a couple of you asked me, hey, you said, where did the 2 minutes come from? and I believe I told you it was just a random example. Just could be whatever. A Riemann sum is a formalized process for doing the integration so that all of you end up doing it the same way. So you're expected to follow the Riemann process so that when the grader grades the AP test, it's not all different, okay? So you have to know how to do a left Riemann sum. You also have to know how to do a right Riemann sum, and a midpoint Riemann sum, and a trapezoidal Riemann sum. And that's the end. I am not being. And that is the end of the list.
I'm literally shaking right now.
Porter, please.
So if we don't use the Riemann sums, will we not get the point on
You are correct. Yeah. So if you do a really good logical approximation, but it isn't a left Riemann sum, they won't give you any points.
But if you just know and like you don't show your work, then isn't that legal? Like,
Oh, in this particular case,
you won't be able to.
good question, 2 points. Okay, the wording here is not mine. I copied it directly from an AP test. And if you don't show computations appropriately, they won't give you points. So I'll demonstrate how to do that. Okay, once again, please, everybody. Make sure you don't just copy how I do a left Riemann sum. Make sure the method makes sense to you. If the method makes sense, learning right, midpoint, and trapezoidal is really easy. If all you do is copy, it's really hard. So just follow the process and make sense of it. First of all, in our class, we are only using Riemann sums to approximate integrals. So don't go doing a Riemann sum unless you know what integral you're approximating. It doesn't make any sense. It's like doing a sign chart and not knowing why. It just leads to chaos. So I'm approximating this integral in this particular example. So on your paper, write down the integral. There are many AP written questions where if you do not write the integral, you lose a point. Basically, 1% of your test is lost just for not writing the integral. Okay, since the test is 108 points, every point's about 1%, pretty close. Okay, Riemann sum is an approximation of an integral. Later in this class, we will learn how to do the integral exactly, no error. But because this is an approximation, don't write equal, write approximately. Okay, here's how the process works. It's very similar to what I've already shown you. It's like, don't talk to me. Oh. I thought it was more like me. Like I'd be in class, and my friend would start to talk to me, like, shut up, I gotta listen. Hey, we're going from time 0 to time 40. So the next thing you're going to do is go up to the table and mark off time 0 to time 40. If you do this, I can virtually guarantee you will walk up to my desk during the test and you'll say, there's something wrong with this problem, it doesn't work. And I will avoid the temptation to cynically say, no, you don't work. Okay?
No chill at all. Like you're struggling to get by. We don't understand calculus because that's just going to do us.
Watch. I'm serious. Every year I tell every class, as you're doing a Riemann sum, do not mark the table like this. It will lead to confusion. Like during the test, you'll feel like the problem is broken. And I'm trying really hard not to say, no, you're broken. Okay.
Oh,
please,
You are.
Why would you ever mark a table like that?
Just because people say, okay, look, this is really kind of silly what I'm showing you, but it really does help. People just say, well, it starts at 0 and ends at 40. And that makes sense. It really does. But it does lead to confusion. So instead of marking in that manner, do it this way and you won't have any trouble. Say we start right here at 0. It's kind of goofy, but it really does help. Just put the mark in the middle of the box. It makes a big difference. We're starting at time 0. We're ending at time 40. Question. Okay? Look, the instructions say, do a left Riemann sum. The keywords are left. Riemann really isn't that key because for our class, we don't learn any other method. So it's always Riemann sum for approximating an integral. The left is key because I got to make sure I'm not doing right, midpoint, or trapezoidal.
Right.
Yeah.
I mean, left.
Yes, good.
My bad.
The other keyword is 4 subintervals, so 4 is key.
But
And the last keyword is of equal length. Okay? So I need to put some more marks on my table. Please raise your hand if you can anticipate where I'm going to put some marks based on those instructions. I'm supposed to do the integral from 0 to 40. I'm supposed to have 4 subintervals of equal length as indicated by the data in the table. So please show me your hand. Talk to each other. Get some more hands up here. Where do I want some marks? This unit is actually a lot of ways, it's a good unit because you can practice it around more. Hands up. Joe, where do I put some marks?
T equals 10, 20, 30.
Oh, so Steve.
Perfect.
okay, never mind.
That's why the middle thing helps.
Yeah, it messes up if you don't put it in the middle.
Okay.
See why, Jonathan?
Yeah.
Yeah, people get all confused. They start putting the lines between. So, please.
Then why did it say left?
What does the left mean? I haven't explained that yet, so you're okay. How many knew I was going to put marks there? Show me hands. Come on. 2 more. Questions? Yep. You want to talk? Oh, Grace is a great example of this. Speak up. Great.
My name's Shirley.
Dang!
Wow, Smith. We're halfway through the year.
Oh.
It's like a parent.
I have like 3 classes.
It's like a fine. It's very sad. Have your parents ever called you by the
Oh,
name?
yeah. All the
It's the
time.
same.
I have 10 siblings.
230 children. I take Shirley, break.
Yeah, I don't think any
Good job.
I'm just confused why it's not. You said you haven't explained the left thing.
The left hasn't shown up yet, so you're okay. Like all we're worrying about right now is that we need to go from time equals 0 to time equals 40, and we have to divide those 40 minutes into 10 equal blocks. Sorry, 4 equal blocks, so each block is 10 long. I said,
Oh, right.
Yeah, my bad. That's still stinging from the mistake.
It's okay.
Please.
So is the only reason we know where we can split them is because it says equal length?
Yes.
Okay,
So, no, go ahead. Go ahead.
if it didn't say that, the other questions that don't say equal length, they're just still solved like the intervals.
Here's the answer to that question. For the AP test, they will always specify left, right, midpoint, or trapezoidal. And they will always specify the number of subintervals. And they'll give enough information so you can determine what those subintervals should be. Okay, so they'll just tell you. So. Please.
So does it not matter like the actual amount that's in between it? Because like when you go from 0 to 10, it goes up 2.5, like on the board.
Oh, gotcha. I see your question. You're doing great. So we don't care at all how much the velocity is changing within the subinterval. If the velocity changes a lot, it means our estimate is not as good. But that's not anything they concern you with during the test. So don't care. Good question. Yeah. Okay. Next step. Look at the symbol. The symbol tells you what to do. We are supposed to take a velocity, and we're supposed to multiply by a change in time. Okay? Ideally, we would do this for every single velocity that is shown. Every velocity. How many velocities are depicted in this picture? Infinite. Infinite. Finite? Infinite, that's funny. Okay.
We're like, that is fine.
That's not what I Okay. Look. Quiet. Okay, ideally when you do an integral, you would take the very first velocity and you multiply by an infinitesimal change in time. Then you take the very next velocity and do it again. But that would be an infinite number of computations. That's why the Riemann sum is an approximation. Because instead of doing an infinite number of computations, you're doing 4. Hence, not as accurate. But the idea is the same. You look at the first subinterval. There are still an infinite number of velocities within that subinterval. But because we're doing a left Riemann sum, which velocity do you pick?
The left.
The left. This is not meant to be difficult. So what is the velocity that is on the left side of the subinterval?
7.
Louder.
7.
7.
6. 5.
Oh, wow.
We want to talk about that. Okay, dt means change in time. Ideally, it's an infinitesimal change in time, but we're doing an approximation. So for that first subinterval, the time begins at 0, ends at 10. So how much does the time change for that subinterval? 10 minutes. So our approximation is that during those first 10 minutes, the position of the object will move to the right by 70 minute miles.
So why are you taking only, I mean, since you're doing left Riemann sum, why are you not taking like 0 to 5, like that change? Because it's the left side. Like, that doesn't really make sense.
Say it again.
So since you're taking the left just 7, then why are you only doing 7 for the max for all of the time of the subinterval?
Gotcha.
Oh wait, because of that last graph you showed us where you continue. Oh.
Yeah, we basically say we're just going to assume that for the entire 10 minutes the velocity is 7. That's all. And the only reason I'm doing it for 10 minutes is because they told me to use 10 minutes. That's all. Other questions? 2 for 4. So here's my advice. Listen, I want all eyes on me now. Look up, Stephen, look up, Ryan, look up. Huge advice here. We are entering the portion of the AP test where lots of problems involve units. If you will learn to check, if you'll just develop the habit of checking your units, making sure they work properly, you'll get a much better score on the test. Guaranteed. So I don't write them out all the time, but I do check them. So I notice that when these two multiply, the minutes divide, and I'm left with 70 miles. That's what I expect, because I'm trying to find change in position.
So like if the next time when you were doing it, you could do like, if you did 9.5, you could just say 95 minutes. I mean 95 miles.
No, Nikki, I do exactly what you said. Just like that. I've checked the units once. I know the rest of it's going to be the same, so I'm okay.
So they don't require you to do that there.
They do not require any units here. That's just me saying that's a good habit.
Okay.
And Nikki, even if all you do is this mentally, that's all you got to do. Just make sure you're checking. People who don't check the units, they make more mistakes. Questions? 2 for Nikki. Please. Hey, no one talk. I can't hear.
Would it be 9.5 times 20? Or
Let me say it back to you. So we're going to the second subinterval. The velocity that is most left within the subinterval is, but this change in time is still 10. It's very good. Yeah, dt means change in time.
Right.
Anybody else? So raise your hand, please, if you know what I need to write next. Just making sure. I get this is going slow for some people, but I can't spend too much time. It's a third of the test, these ideas. So, Adam?
It would be 4.5 times 20 miles. I mean times 10, sorry.
You're good, no worries. How many knew it? 2 points. Questions? Hands up, what's the next one? Just giving some more points away. Giving away points now. What's the next one, Ethan?
2.4 times 10.
How many knew it? 2 points. The next question is a trick question. The next question is a trick. If you understand why I say it's a trick, then I know you're following my thinking. 1 second, Josh, sorry. Oh, you're good. What do I write next? This is a trick question. What gets written next?
Nothing, because 7.3 times 0 is just 0.
Well done. We don't count the 7.3 because for this last subinterval, we're assuming that the velocity is going to stay 2.4 for the entire 10 minutes. So these other numbers just don't come into play. Like we're done. We've done the 4 computations for subintervals. How many knew it? 2 points. Jonathan, please.
So if we were doing a right Riemann sum, then we would ignore the 7.0.
Perfect. Watch what Jonathan said. If this were a right, look close at the board. If we were doing a right Riemann sum, here's what would have happened. These would all be 10 still, because the change in time for each subinterval would still be 10. But this number would have been 9.5, because you would look at the first subinterval and you would pick the velocity that is most right within the subinterval. Question. The next number would be, what would this one be? 4.5. This one would be 2.4. This one would be 7.3.
So would it be beneficial for a right Riemann sum to work from the right?
Good question. 2 points. I find that leads to errors, so I don't recommend that. Even though the computations come out the same, the logic of what you're doing starts to fall apart, because we really are integrating from 0 to 40 like this direction. Going backwards will tend to lead to mistakes. So, good point. Anybody else? Hands up if you know what would get written if you're doing a midpoint sum. Don't overthink it. Just think of the word. Don't overthink it. What would we write if we're doing a midpoint sum? Miranda, what would go here?
9.2, and then 7, and 2.4, 12.3.
How many knew it? 2 points. If we need me to repeat, just wave at me. Just waving. Sorry, please.
And then when is that over the other, this is still be 10?
Right, because even if we're doing a midpoint sum, if they've specified 4 subintervals, each subinterval still has to be 10 long. So the change in time is still 10. We're just picking a different velocity. Please.
What about that trapezoidal?
Okay, trapezoidal is here's what happens on trapezoidal. 2 for Josh. You still go to the first subinterval, same as before, but instead of picking the value that is on the left, or picking the value that is on the right, or the value that is in the middle, you actually take left and right. We add them together, divide by 2. We're averaging the left and right. So we get this new velocity that's representative of the entire time period. It's the average of the left and right velocities. I'll show you that in a second. Good question, 2 points. So you average left and right and divide by 2. That's what goes here. Still multiply by 10.
Is there a reason you don't have the middle one also?
Only because that's how they specified it. Like they could, and I don't know all the different methods that are out there. I know Riemann's one method, there are others. You could say, well, let's do the one where we average all 3. Nothing wrong with that. It's perfectly logical. It's just not the trapezoidal Riemann sum. So, 2 points. Anybody else? Everybody good? Hey, any question about Riemann sum? This one always comes up, so I'll just, no one else here thought of it. Maybe you are, I don't know. If the subinterval is only from 0 to 5, what do you choose if they ask for a midpoint sum? Trick question. the subinterval 0 to 5, they won't ask that. Okay, they won't. Like they'll set it up so you can see the middle point. If there's no middle point, they won't ask for midpoint.
But if the interval was 0 to 5, they could ask for a trapezoidal.
For sure. Very good, 2 for Tyler. 0 to 5 trapezoidal, I still have a left and a right. So there's no way for them to mess it up with trapezoidal because there's always a left and a right.
What if it was 0 to 10? There's 3 of them. That's still over trapezoidal too?
Oh, well, okay, no, good point. If I were integrating from 0 to 10 with this table, they could not specify anything other than one subinterval or 2 subintervals. Yeah, there's no way to specify 2.
Could they get like a midpoint on like an interval of 2 if it was like a graph?
Yes.
Like if the interval was like from 0 to 5, then they could do 2.5.
You'd have to find the value of the velocity at 2.5. Well done. 2 points. Please.
So is the trapezoidal one a more accurate
Approximation. The trapezoidal is typically the most accurate because instead of using one velocity, you're using 2. Just like I was saying to Joe, that's completely logical. It's just not what's defined as a trapezoidal Riemann sum. I don't know. I know there are other ones. We just don't learn them. So.
My name's Josh.
Oh, I was talking with Joseph. Joe was in the that one is clean. I'm good there. Not a mistake.
He was just going to try to catch it.
Nikki, please.
Will they always make the sub-intervals work too?
Say it louder.
Will they always make the sub-intervals work too? They said 4 even pieces and it like worked out.
Oh, yeah, it always works out. Yeah. They'll do creative things, but to test it, okay, they will do creative ways of describing the subintervals to make sure that you're not just memorizing, you're thinking, but it always works out. Yeah. Don't need to worry about that. Please, Austin.
Will they give you like a formula and then ask for this for subinterval?
Very rare, but I have seen it happen, where they ask you to do a Riemann sum. There is no table, there's just a formula. The one I saw was the formula was f of x equals x squared. So not really complicated, but you still had to do the Riemann approximation with that formula. So. You create a table. Right, so they say, hey, f of x is x squared. So you can create the table you need.
And it would give you the...
Right, give enough information about the width and the subintervals and such that you know what kind of size of table to create. Does that make sense? Cool. 2 for each. Anybody else? All right, next thing. Did anybody compute this number for me? 234. 234. You notice it says right here, include correct units. Okay? Listen, I have seen AP questions very similar to this one. Not identical, but awfully similar. Where they would award you 3 points. That means 3% of the entire AP test is going to be awarded right here. They give you 1 point if you remember to write the integral. So don't forget to write the integral. They give you another point if you have these computations listed correctly. And they give you a 3rd point if you write the word miles.
So you put equals 234 for
Yeah, they do that as well in the AP test. Here's why. 2 for column. It's a little bit weird, but here's the logic. The integral is approximately the same as these series of computations. You got it now, but these series of computations are precisely 234%.
So if I were to switch like 4.5 times 10 and 9.5 times 10, I would have gotten that wrong.
Say it one more time.
So like if I switch the placement.
Oh, the order.
No.
No, they can't dock you for that.
Okay.
Because the math is the same if you accidentally kind of get the order wrong. So that you don't need to stress on that one. 2 for Josh. You good? Okay, hands up if you know what this means. You can't lose the meaning. What is the 234 miles representing? You cannot lose the story. Got to keep track of the story, Jock.
It's like the change in velocity.
Close, but not quite. It's not the change in velocity, 2 for Jock. What does the 234 represent? It's not change in velocity. What is the 234 representing? Displacement or change in position. No worries. How many knew it? 2 points. Okay. Yeah, change in position. Cool. Next thing says, use the graph above to illustrate what the left Riemann sum approximation of the integral looks like visually on the graph. So we're trying to depict what these computations will look like over here. Understanding the graphical connection is a big idea. You've got to make sure this makes sense as well. All we're doing is pretending the velocity stays at 7 for 10 minutes. That's easy. Then we're multiplying the velocity by 10 minutes. So the velocity is this dimension right here. It's the length of this blue line. This line has a length of 7 miles per minute. I guess it's a red line now, sorry. So that line's length is 7 long. That gets multiplied by a change in time of 10. Okay? This computation is graphically represented as an area on this picture, because you have this dimension multiplied by this dimension. So it is important to know that that's just an area. Questions? Like, you get tested on that. So if we did the integration perfectly, here's what would have happened. We would have created a very thin rectangle right here. That's not very thin. Let's try again. So we create a thin rectangle here. That's too thin. I feel like the Goldilocks story. It's not going to work, I don't think. It'll have to do. It's not too bad. Okay, so we pretend that's very narrow. So you take the velocity multiplied by a small amount of time. Then you repeat the process. So you go to the next velocity, multiplied by a small amount of time. You get very narrow rectangular areas. You add up all those little narrow rectangles, that's the value of the integral. So if we can do the integral perfectly, the area that gets computed follows the curve. That's a pretty good drawing.
So you're just finding the area of...
You're finding the area between the curve and the x-axis. And that's what's happening here. That's the connection. Okay, so what I always teach, some teachers will say integration means find area. It doesn't. Integration means to multiply and then add them up. But you can use it to find area. So the connection is important. Question? Okay, look at the picture. You should be able to tell me very quickly. This little computation, 7 times 10 is saying that during the first 10 minutes, the position will change by 70 miles. Is that an over or under estimate? Say it.
Under.
Louder?
Under.
Under. You can see the perfect computation would have found an area like that. That would be the area we would compute if we could do the integral without any error. We only found the area here, hence we are finding an underestimate. At least for that section. As we move over, it changes. So the next section, we took 9.5 and we multiplied by 10. So that's this one. So that one's an overestimate. Questions? Next one is 4.5 times 10. Also an overestimate. Last one is 2.4 times 10. Underestimate. Overall, we're actually pretty good. So we kind of balance between over and underestimate. So if you can compute the areas perfectly, you can see exactly what the error is. Questions? Please.
Is it just a coincidence that like the over and the unders look pretty similar?
Like it balances out?
Yeah.
Mostly because the graph I drew has some symmetry to it, but otherwise just coincidence. 2 points. Please.
When we use calculators, will we be able to figure out the exact amount of change?
Awesome. I'd like everyone to answer this. Points for everybody. It's a really good question. 3 for Joe. 4. Mark down 5.
7.
5. Okay.
Good job.
I appreciate it.
We're so
Okay.
ungrateful.
The question said, if we use a calculator, can we do the integral perfectly? Raise your hand if you know the answer. If we use a calculator, now what the calculator will do is it will find the velocity right here, multiply by 0.00001, find the next velocity, multiply by 0.00001. So will the calculator do a perfect computation of the integral? Yes, no, and why, of course. Ethan.
I think no, because you're doing integrals still, so it's super close, like super close. But
Yeah, you're still, like how many computations do you have to do to make it perfect? Infinite. So the calculator does like 1,000,000, which is a lot compared to our 4. Me too. I ain't doing no million. Yeah, that was for dramatic effect. Also, that's funny. Dramatic effect. That's good. Everyone's going to express Aspen Hopkins told me this morning I'm supposed to go like this. I don't know what that means. Never mind. Okay. Is that some sort of thing?
No,
That sounds like Aspen.
No, it's
Sounds
not.
like Mario.
Aspen's just
Aspen.
Yeah.
Figures. Okay. To be expected. So, no, the calculator is not perfect either, but it's really good. Okay. We will learn eventually. Good job. No homework tonight. So. Hey, listen. Waiting for the sidewalk. Okay, we will learn what I believe Isaac Newton discovered, which is, well, you already know that. So. Isaac Newton discovered a lot of things. He was, quite the guy. He figured out that there is another way to compute an integral. So instead of adding up, 1,000,000 computations, he figured out another way to do it, and it turns out to be perfect. So he figured out a way to add up 1,000,000 different things in a different way, and it works perfectly. So we will learn a way to find the integral exactly.
What is it? Is it a formula?
It's not really a formula, more of a process. So it takes a little while to
from like
explain.
the tree of good and evil. It just hit his head and gave him a little bit.
You do, yeah, the formula. 2 points. Hey, look up. We good here?
Yeah.
Next one. So we already did this as well. This is item 3, part A. So page 3, part A says, rearrange the fundamental theorem to create an equation which can be used to calculate the position of the airplane at 0 minutes. We already did that. We said S sub 0 will equal, take what the position was at the end of the time period and subtract from that how much the position changes in total during the time period. So just another use of the fundamental theorem. Okay, now it says use a right Riemann sum with 3 subintervals of equal length and values from the table to approximate this integral. So you're all going to do that on your own real quick. There's, as I said a minute ago before Colin left, there's no homework tonight. One reason I don't want you doing homework right now is a third of the test involves this big ideas. And I don't want you to get, like sometimes when you do homework at home, you don't mean to, but you teach yourself incorrectly. Okay? So I'm just a little cautious for the next couple of days. I want to make sure you learn it right. So we're just going to do it here. So do that. Go. Do a right Riemann sum approximation of that integral with 3 subintervals of equal length. Show computation. Stop me if you want to ask. Don't know why you're multiplying by 25. Oh, good.
I thought it was still.
Somebody dropped their little case for the headphones. Is that you guys?
Oh, it's always me.
Ah.
Thanks.
Who has that written on their paper? Sure, what number did you get?
45. Wait a minute.
Who has that written on their paper? Show me your hand. Who has that? 2 points. You want to talk about it? Please. They won't dock you, but I wouldn't do it that way. It really does tend to lead to some future mistakes. Like some stuff we do later, that tends to make it confusing. So it is better to go left to right. But they won't dock you. Anybody else? Any questions? Someone please, right? Oh, please, sure.
So, why did you just not write the 2.4 miles over minutes times black miles just because you stopped, like, since we did that last time?
Yeah, I just kind of made sure I checked it visually. I often will check it right here, Shirley. I'll say, hey, I'm going to take miles per minute, multiplied by minutes. Hey, I'm going to get miles. That's what I expect. Please.
So are the AP test graders going to dock you at all if you do like 2.3 instead of 2.4?
Yeah, you lose the point completely.
Okay. So it has to be exactly even decimals. If they didn't give you a table and they just gave you a graph, would you go that
Oh,
backwards?
outstanding. 2 for Tyler and 2 for Joe. Listen, I've never seen them give a question where you were expected to read a graph unless the graph was like clearly denoted in some way as to the exact number you should be reading. Like they won't make it fuzzy. Does that make sense?
Yeah.
Anybody else? Please raise your hand if you can tell me what this represents specifically. Well, I'll pay everybody on this one. What is this that's the most important part, really. Like learning the Riemann sum is just kind of training you to do a process. But Grace, what does this mean specifically? It's the displacement for what time period?
From 20 to 35.
Perfect. So my object was somewhere. 15 minutes go by, the object's somewhere else. that space is 45.5 miles. How many knew it? 2 points. Josh, question?
I was really
Very good. Ethan? Oh, no, you're good. Anybody else? Well, this is a typo. This should say right. I didn't expect you to do a different integral. So if you're
do that?
no, in fact, hey, I try to always be straight with you, not deceptive in any way. I've never seen an AP question that asks this part C, but I did need to find a way to help you see the connection. So this is just to help you see the connections. So I'd go, let's see, 20 was 2.4, so that means I'd be like this. And the next section is 2.4 again. The next section is going to be 4.3. This one's pretty close, but I'd like to see what you think. Please raise your hand. Do you think we are finding, is this just based on what you see, what's your best guesstimate? Is this, just raise your hand, is this an over or underestimate? Come on, hands up. They do ask that question. They'll say, is it an over or underestimate? That's a common question. So this one's pretty tough, but just kind of want to know what you think. Can't really tell for certain, but I feel pretty good about my answer. Over or underestimate? Mason?
Under.
Tell me why.
Oh. I don't know.
You're okay. So if we did the integral, 2 points for Mason. If we did the integral perfectly, we'd be finding the area that I'm going to highlight in blue. That would be the area that the integral would compute if we were doing the integral perfectly. Instead, we did the pink rectangles. So hands up, you think it's an over or underestimate? Let's go Miranda. I think this one's, how many thought it was over? Woo, 2 points. I thought it was over because I kind of felt like this shape here is pretty close to this thing. And then we just have a little bit too much there. So, question?
Wait,
hey, oh yeah, please.
Will they ever ask what you're asking?
No homework tonight, remember, no homework.
Overestimate or underestimate?
Oh, always, that's common. They don't usually make it tricky, they make it a little more obvious. But, like, that's not too bad, but usually they're a little more obvious.
And,
yeah, 2:30 to 4:30.
What if you can't stay the whole time?
You just stay with me. So in term 1, I kind of made the retake cup a little more formal to get people used to what I expect. Not even with me for a semester, I just have one.
You only have to do 2.
So on A days, that's my prep. On B days, I have class.
I'll have to do the retake if I haven't taken the test yet.
I got 79, so I'm like, I guess I'll retake it.
Highly likely, always watching.
If you mind, give me a holler.
Yeah, I think it is.
Oh, freak yeah, dude.
I think we'll actually be able to finish that next time. Yeah, we're getting enough of the bulk of it, the rest of it will go faster now. So.
I'm not even.
Oh, you're lying.
I'm really not. Bruce, no worries. Thank you. Check that at 10:20. So I can try to-
Conveniently, so you just commit 7 right on